Question number 15 from section 4.5. We're asked to solve the equation natural log of the quantity 9x plus 7 minus the natural log of x equals the natural log of 10. Now we have these two logarithms that are split with a minus sign. We're using this property of logs to condense it into a single logarithm. This is ln, the logarithm with a base e, of 9x plus 7 minus the natural log of x. That's going to be the same thing as the natural log of 9x plus 7 over x, using that quotient property of exponents. And then on the right side, we have the natural log of 10. Now take a look carefully at this equation, because we have an equation that has a natural log on the left and a natural log on the right. We have an argument on the left and an argument on the right. Well, if both sides are natural log and the equation is equal, then the arguments have to be equal. It's, in this case, it's almost like we're dropping out those natural logs and writing a brand new equation as 9x plus 7 over x is equal to 10. See, if the natural log is the same as the natural log on the right, the natural log on the left is the same thing as the natural log on the right, then the argument on the left has to equal the argument on the right. So it's like we're dropping out those natural logs. So we get this equation 9x plus 7 over x equals 10. We can solve this equation by cross multiplying. A fraction on the left equals a fraction on the right. You can cross multiply. So the equation we can get from this is 1 times 9x plus 7 equals 10 times x. And we can distribute the 1 and get 9x plus 7 equals 10x. And then I'm going to subtract 9x from both sides. And you get 7 equals x. So that's our answer, x equals 7. That's a solution to this logarithmic equation. Okay, we have just a couple more in this section. Looking at question number 16, we want to solve this logarithmic equation. Notice we have two logarithms with the same base that are split with a plus sign. We're using this property of logarithms to condense it into a single logarithm. So this is going to look like log base 3 of x plus 12 plus log base 3 of x minus 12. When we condense it, we're going to multiply the arguments together. So this is going to be x plus 12 times x minus 12. That's one big argument now, equals 4. Let's simplify this. So we can write it as log base 3. Now if you use FOIL here, x times x is x squared. The outer is minus 12x, the inner is plus 12x. That's going to cancel out, and then minus 144. So log base 3 of x squared minus 144 is equal to 4. Now we have a logarithmic equation. It's in this form. We have a base, an argument, and an exponent. We can convert it to exponential form to solve for x. The base is 3. 3 raised to the 4th power is equal to the argument x squared minus 144. Well, 3 to the 4th power is 81. So we get 81 is equal to x squared minus 144. We want to solve this for x. I'm going to add 144 to both sides. Moving this other part over a little bit. Okay, we get the equation 81 plus 144. That's going to be 225 is equal to x squared. Now when we solve this for x, we can take the square root of both sides. Square root of 225, I believe that's 15. So we get x equals square root of 225 is 15, but because this is a square root of the x squared, x could be either plus or minus 15. You do want to check the answers for here. If you plug in positive 15 into the original equation for x, you get positive arguments. But if you plug in negative 15, you end up with a negative argument, and that's one of the rules when you're dealing with logarithms, that the argument can never be negative. It has to be positive. So x equals 15 is the only solution. We can eliminate x equals negative 15. Okay, so we use the properties of logs to condense the two separated logarithms into a single logarithm. And then once you get into logarithmic form with a single base, argument, and exponent, convert to exponential form and use algebra to solve. Then we had to check to make sure that if we plug in our answers into the logarithmic equation, that the arguments are going to be positive. So we eliminated x equals negative 15 as a choice. And then finally, question number 17. How much money will there be in an account at the end of 8 years if $6,000 is deposited at 4% interest compounded semi-annually? This is a compound interest. We have $6,000, that's how much we're going to deposit initially. We're going to use the equation given here. A equals P times 1 plus R over N to the NT. Now we have some numbers here. The first number I see is 8. So let's say that's 8 years. So we can say T is going to equal 8 years. The next number I see is $6,000. That's how much you're going to deposit. That's your present value. So P is equal to $6,000. The next number I see is 4%. That's your rate, interest rate. So we're going to let R equal 4% as a decimal is 0.04. And then the next thing I see here that's going to give us something, a value to plug in, is a semi-annually. Semi means half. Half annual, every half of a year. So the number of compounding periods in a year, N, is going to equal 2. Semi-annually means every half year, so that's going to be twice a year where the interest is compounded. Now you can plug in everything that you know into this A equals P times 1 plus R over N to the NT power. We get A equals 6,000. 1 plus 0.04 divided by 2 raised to the 2 times 8 power. I do like to put parentheses around that entire exponent, and you do need a calculator, either scientific or graphing, to compute 6,000 times 1 plus 0.04 divided by 2. Then I close the parentheses and raise that to the 2 times 8 power. I go ahead and add parentheses around the exponent. So we get that if you deposit $6,000 at the end of 8 years at 4% compounded semi-annually, the amount of money that will be accumulated is $8,236.71. Notice that I round to 2 decimal places because we're talking about money here. Round to the nearest cent. And check your answer.